Okay, thanks, Mac. So as Mac said, my name's Ben, and today I'm here to talk to you about Rust. So that's not the Rust you see on your car. This is actually the programming language Rust. So just out of curiosity, has anybody here heard of Rust before? How many people here have used Rust? Okay, a few. And how about C or C++, those kind of languages? And how many of you are willing to respond to my questions? Cool, got a baseline set. All right, so we've got a bit of a short time slot, so I'm going to try and get as much clarity through as possible, perhaps at the sacrifice of correctness. So bear with me for that, and at the end of the talk, there's going to be time for questions, and you can hunt me down during the conference, and I'll be happy to talk to you more about Rust. So I'm going to, for the sake of clarity, I'm going to try and avoid any code snippets. I'm going to talk about the core concepts. But just as a warning, I am going to talk a little bit about memory management stuff. So there's your warning. So first of all, what is Rust? Rust is a compiled language, and it's fairly new. The 1.0 version of Rust just came out this past May. It was created by Mozilla with the intention of using it for their new browser rendering engine, Servo. Although right now Rust is largely being driven by the community. It's a very strong community that is driving the growth of the language. And Rust is a systems programming language, which means it gives you a high level of control, which is kind of like the C, C++ languages. But it also provides you a high level of safety, which I'm told is a little bit more like Haskell on that end of the spectrum for languages. And not only does it provide you that safety, it does so at compile time. So if you do anything weird, it's going to tell you right at the compiler that this line of code is bad, please change this. And it can do all that without necessarily using a runtime or garbage collector, which is pretty sweet. So as I mentioned, languages typically fall on one end of the spectrum of either control or safety, maybe somewhere in between. But typically there's some pretty strong trade-offs. And with Rust, they try to encompass all of the control and all of the safety all in one language at once, which is pretty awesome. So there's a ton of awesome features in Rust, but again, this is a short talk, so I'm not going to get into everything. There's things like variables must be initialized when you declare them. Variables are immutable by default. There's no concept of null, and there's a huge list of really awesome things in Rust. And I'm not going to get into all of these. But I am going to talk about one thing in Rust that is particularly awesome, and that is the concept of ownership. And the ownership system in Rust is really what gives you all of that safety at compile time, and it's used for a lot of those other features I mentioned as well. So this ownership model really helps you guarantee a high level of memory safety in Rust. And so there's various bugs that can come up if you don't manage your memory properly in various languages. Things like dangling pointers, buffer overreads, data races, seg faults, that kind of stuff. And Rust can essentially eliminate a bunch of these things just by having its ownership system active in the compiler. So why don't we quickly go through an example of how one of these bugs might occur. We'll use the dangling pointer as an example. And so you can imagine this example is written in something like C++. We're going to create a vector, which is a growable array of data. And so on the left in the gray, we have our stack memory. We've got a pointer pointing to our heap allocated array, and then we've got our size and the length of data that's used in that array. So it's all pretty straightforward so far. Now let's say we want to pass this vector we've created into another function. So when we do this, we're going to copy our stack memory into the memory context of the function, and that pointer is pointing to the same place in the heap. So we're sharing that memory, the heap memory, which could be 2 pieces of data, it could be 2 million pieces of data, it doesn't really matter. The copying action is the same size, which makes it really fast, and this is the same kind of thing that Rust does. But again, we're just focusing on how the bug would occur in C++ for now. So what happens if we try and push some data onto our vector? We've got to reallocate our space because we didn't have enough free room. So we've deallocated the original memory, and now we've got a new chunk of memory that our current stack is pointing to. Now what happens when this function returns? Our stack goes away, but our heap that we've now really reallocated is just floating there. We've got a memory leak. And now our original context has our pointer pointing into freed memory, and so we're going to have a bug there. So this is exactly what the Rust ownership system is trying to avoid. So, ownership system. I like to describe the ownership system in Rust sort of like how a person might own something. So let's go through an example like that. Let's talk about how someone might own, say, a painting. So if you own a painting, you're totally allowed to look at it whenever you want, and you're totally allowed to modify it if you want. I didn't like the scenery being just regular scenery, so let's throw a monster in there. So when you own something, you're totally free to give that to somebody else and grant them ownership over it, and then it's no longer yours. So we introduce a third party here, give them the painting, and now I'm not allowed to do anything with it unless I get strict permission from this new person. If I go away, the painting is still with the new owner, and everything's fine. And if this owner goes away, then the painting is immediately destroyed, just like in real life. So this is essentially what happens in Rust. As soon as an owner goes away, then the memory that is allocated with that owner also goes away at the exact same time. The compiler is able to detect when something goes away and immediately inserts that memory freeing call. And so in languages like C and C++, you have to specifically free memory when you're done with it, which can lead to you forgetting or you doing it twice and causing bugs that way. And Rust just kind of does that all for you, but it gives you the same kind of speed of a program as you would if you had written it manually, which is pretty great. This also gives you the advantage that you don't need to have a garbage collector. So with a garbage collector, it keeps you from having to write all that manual code, which is one good thing, but the memory doesn't get freed immediately, and so that can sit there and have a little bit of a leak temporarily, and then it might, the runtime might go ahead and start clearing away the code, or the memory, I should say, when you're trying to do something that's maybe a little bit more tight with timing. And so by having it cleared right away, you know that this is always going to happen right here, and nothing's going to get interrupted at a bad point. So that's pretty great. So now there are probably times when you might own something and you might want to lend it out to somebody and then still have ownership so you can have it again later on because you still want to use it. So Rust has a system that takes care of this too. It's called the borrowing system. In languages like C++, it does very similar things with just function pointers, or sorry, memory pointers. Rust has the same concept, but it's a little bit stricter when the compiler gets its hands on it. There's two different types of borrows in Rust, which is where it kind of differs from C++. You can have a mutable pointer, or a mutable borrow, and there's also a shared borrow. And so let's get into what those two things are. Let's start with the mutable borrow. So when you have your painting, let's say you want to loan it out to somebody, and you want them to be able to modify it. So in this case, we're going to maybe give it to someone who specializes in restoring paintings. Someone's gone and painted monsters all over our paintings, so we're going to see if they can fix it up for us. So we're going to lend out our painting to this restoration specialist. Once I've loaned it out, I no longer have access to the painting. I can't look at it, I can't modify it. The person who's restoring it doesn't like people looking over his shoulder while he's working, so I'm sure we all get that. So he's working on this thing, we can't touch it. But if he wants, he can now pass it off to somebody else, and then they can modify it. Let's say he needs someone to reframe the painting, he can't do that. So he's going to pass it off to someone who can reframe it, and then he can no longer work with the painting either. And eventually the framer is done with it, it goes back to the restoration person, they leave, and we got our painting back. And then we're free to do what we want with it again. So that's all pretty straightforward. So now let's talk about the shared borrow in Rust. So let's say we wanted to give our memory out to multiple places at once, and they all want to read from it and do different things. That's what this will help us solve. So in the painting example, we have our painting, and we want to share it with a whole bunch of our friends. And so we can put it on display on the wall, and we can invite people over, and if they want, they can invite more people over, and eventually there's a whole bunch of people there that are coming and looking at our painting. And it's great, they can all look at it all at once, it's not going to cause any issues. The painting is hanging on the wall, it's out of reach, so no one's able to mess with it. And so that's essentially what the Rust compiler does here too. It allows you to share things out, and if you're sharing it out in a broad sense, then it will prevent anything from modifying it and causing issues with someone else that might be reading it. Now, the difference where these two borrows are different from C++ is in C++, both those borrows kind of happen at once. So it's kind of like having your painting, but instead of hanging on the wall, you're just going to throw it on the floor in front of everybody. And as they walk in, you're going to hand them all spray paint. And then you're going to walk out and hope that they just do the right thing. And so in those languages, there's no guarantee that anything correct is going to happen. So it's all up to the developer having strict guidelines and patterns that they can follow. Meanwhile, in Rust, all of these patterns are codified and they're in the compiler and they're guaranteed to run every time you run your compiler. And if it doesn't work, you don't get a binary. So it's very, very nice. You get that very quick feedback. No bugs get introduced into the actual published code. So let's take what we've learned about borrowing and ownership and see how that same dangling pointer bug, how that would have played out if we had written that code in Rust. So we're going to start off the same way. We have our vector that we've created. We've got some stack memory and some heap memory. And now we want to pass that into a function again. So how we're going to call a function in Rust when we're transferring ownership is very similar to how we would transfer a variable in other languages. We just call it in our function. And so we copy our stack memory into our new context. But you'll note that the original stack context is grayed out now. And I'll get back to that in a second. So in our function, we're going to push a new element to our array. We're going to reallocate it again, same as before. But now our function is going to return. And since the owner of that vector has gone away, we've immediately freed the memory, which is different from before. We've also, since we've transferred ownership into that function, our original context did not have access to that stack memory anymore. So if we were to try and access that stack memory again, try and use that same variable, the compiler would block it right there and say, no, your code's not allowed to do this. And it totally prevents this same bug from popping up again. Now again, I mentioned that sometimes we might want to loan something out and have it modified and then have access to it again. So in other languages, we would use a pointer. And in Rust, it's the same way. So this next example we'll go through with a mutable borrow in Rust. So to do that, to pass it into a function as a mutable borrow, we use an ampersand to show that it's a borrow, and we say mute just to say that it's a mutable borrow. And instead of copying the data from the stack, we're going to create a reference back to the original stack memory. If we need to push something onto the array, we reallocate it. And when we return, then we just have access to our stack memory again. And so we can see that we've got our new allocated memory totally accessible from our original context. And so far, this is the same in C++ and Rust, but it breaks down once we start doing a shared borrow. So let's look at a shared borrow example. Again, we're going to start with our vector. And we're going to start with a different function. And this time, we're going to pass two vectors into our function. And the function is going to go through and add up all the elements from all the vectors that are passed in and give us a result at the end. And for some reason, we've decided we want to pass the same vector in as both arguments. So we're sharing that one source of memory in two locations. So we're going to create two references pointing back to the original stack. And we can create an iterator that's going to go through and read all the different elements. It'll cycle through, point to the next element. And we can create our iterator through either of the references. And it's totally fine. Everything's just read-only at this point. And nothing's modifying it. And so everything's totally kosher. Nothing's going to break. Now, it gets interesting if we try to add a mutable aspect to this. So let's take a different function. What we want to do is we want to take all the elements from the first vector and push them onto the end of the second vector. Now, in this case, that's something we probably didn't mean to do, but maybe the developer who was writing this code accidentally copied and pasted a variable and didn't change a number or something. And so now we've accidentally pointed the same vector into both arguments. So it's going to try and copy all the elements from the one vector back into itself, which is going to cause some issues, as you'll see in a second. So in C++, that would totally be fine. We try to push our element into the array, we have to grow it, and now we've got an iterator pointing into invalid memory, and even though our vector is pointing to the correct memory. So in Rust, not allowed. We've tried to do a shared borrow at the same time as a mutable borrow for the same chunk of memory, and the compiler just sees that you're trying to do both things at once and says, nope, not going to happen. And Rust compiler errors are really fantastic, and they'll tell you exactly what happened, and they'll show you where to get documentation on how to find out exactly what happened that caused that to go wrong. So, yeah, so that's ownership and borrowing in Rust. There's various other topics that I would have liked to talk about, and I'm going to wrap it up here real quick so that we can have some time for questions if there's anything like that. hopefully you guys have learned something about Rust and you've become interested in writing your next project in Rust. Here's some resources if you want to learn a little bit more. My talk is kind of based on this memory safety in Rust talk. It goes into a lot more detail. It shows some actual code examples and talks about some other concepts as well. So if you want to learn more about the same things I've talked about, you can check that out. If you want to learn how to write code in Rust, there's Rust by Example and the Rust book, which are really fantastic. And these monster paintings are by Driscoll Reed, and that's his website there. So, yeah, so thanks for listening to my talk. And yeah. I think we still have some time for questions, so I see one at the back. In this case, I was specifically talking about single-threaded applications. One thing I probably should have added to this was that Rust was developed for multi-threaded applications as well. And this borrowing system actually makes multi-threaded applications really safe as well. So in a single-threaded application, which is my examples, as soon as the function exits, it immediately has to return its lock on that code, or on that memory. So it owns the pointer to memory, and then as soon as the function returns, its ownership of that pointer goes away, so that pointer is freed, and then the code goes back and has access to that memory again. Yeah. Mm-hmm. Yeah. Sure. Yeah. So the question was, what happens if things are borrowed and the original owner of the resource goes away and the borrow is still active? And so that's a more complicated topic in Rust. That's referred to as lifetimes. So I kind of glossed over. Like I said, I was going to go for clarity over correctness. So when I said that when the function returns, everything goes away at that point. Really, what happens is the lifetime for that variable. It's reached the end of its lifetime, and so Rust knows that it's able to free it at that point. In Rust, you can actually manually declare how long a resource is going to survive, and if something tries to, if you try to write code that will have something outlive the resource borrow that you've handed out, then the compiler is going to catch that too and say, no, this lifetime isn't as long as this lifetime. You need to fix your code and make it so that your resource has a shorter lifetime than the owner of that resource. Does that make sense? Yeah. Yeah, it's a more complicated concept, so I didn't want to try and cram it into this short talk, but it's pretty interesting how it just kind of does it for you a lot of the time. Yeah. I see a hand back there. Yeah. Yeah, so the question was, how does this affect compile time? Right now, Rust is still fairly new, and so they haven't spent tons of time working on compiler optimizations. However, it is LLVM backed, so any optimizations that are built into LLVM, you get that automatically by using Rust. So there's still some optimizations that can be done to get the special parts of Rust to compile faster. And that's one of the things that they're working on now that they've got their official 1.0 release and things are stable. Prior to that, there was a lot of churn in how things looked. So that's something that's in active development right now. Yeah. Up here? That's an excellent question. How does this work for cross-platform? That's actually one of the things that drew me into this to begin with. Their target audience is C and C++ users. Their goal is for making platforms for the web. They're making a new web browser at Mozilla. For me, I was really interested in it as someone who likes doing embedded electronics. And so I know that that's some place where Rust doesn't have a great foothold yet, but they're working on it. So I know that they do have compilers that will compile to ARM Cortex microcontrollers, and I've done that myself and made blinking lights in Rust, which is pretty awesome. And it works on, you can write programs for Windows and Linux, ARM, x86, 64, all that stuff. So, yeah. Yep.
So if I'm working on my own on something, it's very easy to use for us. But if I'm at a company, like
Sure.
Do you have any comments on how you can maybe update this component
Yep.
or what it adds, what it adds without running?
Yeah. Rust is actually compatible with all those tools because it basically is a very compatible compile system since it's LLVM based. So you get the same objects out at the end. Yeah, the question was, how can you get buy-in for your company? So you can use a lot of the same tools, and you can use a lot of the same existing code base, and you can write new code that can call into your old C and C++ code, and you can get C and C++ code to call into your Rust code. So say you have a critical piece of code that it's written and tested, and it's been deployed, and there's no issues with it, and you don't want to have to rewrite it. You can keep using that same code, call into it, create a safe wrapper around it, and now you can write easy to write safe code that uses your existing library that's been proven. So yeah, at the back there.
Everything is great for security. Is there any other really great Rust that you really like?
Yeah, well, you saw the big list I had that was kind of scrolled off there. So the question was, what else do I like about Rust? Personally, I really like just writing code in it is really fun to do. One thing that it was kind of weird for me the first time I started writing in Rust was they don't have the traditional for loops like you do in C and C++. All for loops are iterator based, which as someone who kind of came from the C++ world was kind of weird. But really it is really nice to know that every time you're looping through something, you're actually looping over like concrete things. And you can manipulate those iterators and do all sorts of fun things, and you get something really great at the end. It's also got a lot of functional tools, so if you like doing functional programming, you are totally able to do that in Rust. Yeah, there's a whole host of things that are really great. Oh, yeah, and I mentioned immutable variables. By default, all variables in Rust are immutable, and so it makes it really easy to make your code. You know exactly what a variable is for. You initialize it, and that is what it holds for the entirety of its lifetime. If you want, you can make it mutable to make changes to it. Maybe you've got a connection to a pipe of some sort, and you need to be able to change some aspects of that as you're running. But generally, when you've got an object, you can, by default, know that it's going to stay exactly as you expect it to be throughout its lifetime. So there's lots of little things like that. So yeah. Anything else? Yeah.
What's your favorite editor?
There you go. That'd be Vim for anybody that can't read. Yeah, okay. Thanks a lot.